All right, as usual, we're going to make sure that we label everything in our comp books. 11, Unit 11, gas laws. All right, so far we have the notes with the relationship between pressure, volume, and temperature. And now we're going to include something called the ideal gas law. Yeah, we're still dealing with all different type of gases, but now we're looking at a relationship that's going to include the number of moles or the number of grams of an actual gas. So I'm going to lay out the actual equation first, and we're going to go through it and label and then attach all of what everything's meant for it. PV is equal to nRT. So PV is equal to nRT. Sometimes we like to make words for types of reactions. And in this case, just like we did the MC delta T, sometimes we called it the MCAT. This PV nRT is sometimes called PIV-NERT. So if you hear the word PIV-NERT, that's usually chemists saying the ideal gas law quickly. Our P variable we've used before, it stands for pressure. So let's label that as pressure. We do have units of pressure that we've labeled before. So I want to give the options of different units of pressure. We have a possibility of atmospheric pressure, which they tend to use when they're in the news, talking about pressure. mmHg is millimeters of mercury. An equivalence to millimeters of mercury is something called torr. It can be capitalized or lowercase, either way, it's acceptable. The values of those are the same, and that's going to be in our future notes in a few minutes. We'll see what that means. kPa is kilopascals, and if we have kilopascals, we can also divide by 1,000 and get our pascals. So units of pressure. We also have the variable that we've used last week. It's volume. The only difference here, oops, let me spell that correctly. The only difference for this volume in our ideal gas law, unlike when we're doing the relationship between volume and temperature or pressure and volume, there we didn't need to convert the volume. We could either have it in centimeters cubed, we could have it in milliliters, as long as it was consistent on both sides. For the PV is equal to nRT ideal gas law, you always need volume in liters, and has something to do with the constant that we're going to be talking about in just a few minutes. Then we have a variable that we've seen before and used. It's called temperature, T. Just as we practiced before in the gas laws, temperature needs to be in Kelvin. To get Kelvin, you take your Celsius and you add 273. So we'll focus to make sure that you continue changing it into Kelvin if it's not in Kelvin already. If the answer is requiring you to answer in temperature, you can just keep everything in Kelvin unless otherwise stated. But for our practice problems that are upcoming, there's no statement that says you need to convert into Celsius. You can leave everything in Kelvin. Okay. So something new so far for the ideal gas law is this volume must be converted into liters. We then have an N, and we have seen N in first semester. This means the number of moles. So maybe I'll bubble over. Let me expand that right here, just to give a little review on moles. Because if we're not given something in moles, but we're given it in grams. So let's say a number of grams, whatever that number may be. 100 grams, 50 grams, 75 grams, whatever that number is, you set up the proportion where you're looking for number of moles. That part of the proportion looks like that. And then with the periodic table, you can set up the second portion of the second part of the proportion. So that would be your mass per 1 mole, okay? And this is known as your molar mass. And you got that using your periodic table. And just a reminder how to convert, because I do have practice problems where I give you the amount of grams of a gas, But in order to utilize this ideal gas law, you'll need to be able to convert into moles. Okay, so reminder of that. Let's box that in because it's important. We've been using it a lot, and we're going to keep using it throughout the rest of the school year. So the only new variable that you have here is the R, and I'm going to use that and write that down. It's called the universal gas constant. And we're going to talk about what that is, which is kind of nice. You see the word constant. That means it's been already solved for us. It's a constant. So I'm going to scroll down a little bit to make myself have a little more room here. And I'm going to talk about that universal gas constant. And I'm going to put down capital R so we know what that stands for. Capital R in organic chemistry was that group that it's attached to anything like amino acid. But capital R in inorganic chemistry is called the universal gas constant. I'm going to define that. So it's used to quantify. There we go. Go back a little bit like that. And it's used to quantify the relationship between the properties of a gas relating to volume, pressure. Divide that out just to show you moles and temperature. Okay, so universal gas constant is to quantify the relationship. So it's taking the relationship between volume, pressure, moles, and temperature. Your volume always having to be in liters, temperature always having to be in Kelvin. So this is the unit that comes out of this universal gas constant. And pressure, well, it varies because you could have a pressure in atmosphere, you can have a pressure in millimeters of mercury, you can have a pressure in torr, you can have pressure in kPa, you can have pressure in PA. In PSI, I haven't even talked about pounds per square inch. However, I've exhausted all those units. I'm just going to focus on the ones that I like to use the most here. And then the number of moles. So what are these constants? And this is really important that you write this portion down. Because in order to solve, you should know the R constant values. All right, so I'm going to scroll up a little bit. I'm just going to move this up slightly here. So now we can look at the R constant. We're looking at what we should be including in our equation. Again, it has a lot to do with, and everything actually to do with, which pressure unit we're using. If we're given a pressure in ATM, so we're asked to solve either volume, moles, or temperature, and we're given the pressure ATM, the R constant for ATM is 0.082, and I'll round it to 1 right here. And the unit is liters times ATM. So liters times ATM, the relationship, divided by moles times Kelvin. So that's the unit that would be using. Again, that's if we were given a pressure in ATM. Well, what happens if we were given a pressure in mmHg or in torr, since they're the same values? The R constant for mmHg or for torr, again, doesn't matter if you capitalize. Oops, I'm off the screen here a little bit. Capitalize or lowercase is acceptable for torr. Both of these are 62.4. So this would be liters times millimeters of mercury all over moles times Kelvin. If it was torr, it's the same value. However, the unit would be torr over moles times Kelvin. So you can see that R constant is dependent on which value, or which unit rather, of pressure you're using. We still have kilopascals. So the R constant for kilopascals is 8.31 liters times kilopascal over moles times Kelvin. And if we have kilopascals, we can have pascals. I'll write it out even though the difference is dividing by 1,000. So we can divide by 1,000, and I'll just keep the 831, move the decimal values over, and I get liters times Pascal divided by moles times Kelvin. Right? These are all the different R constants, and there again are more, but these are the units of pressure that I've been using so far. Okay, I'm going to pause my recording. All right, so we just have a little bit more to go through. We're going to talk about standard conditions, so I'm going to scroll this away here, put this over there. And I'm going to write down on top STP and what it stands for. This means standard temperature and pressure. And we do have to include volume, and so I'll include that. But STP talks about the standard conditions. So standard conditions in Darien, Hinsdale, Illinois, for temperature, it's 273 Kelvin. And I'm going to keep it in Kelvin since everything needs to be converted into Kelvin.
Miss Salkson?
All right, now our standard pressure. In Darien, Illinois, our standard pressure, since we are a certain level above sea level, okay, it's different in Colorado, but in Darien, we're at 1 atmosphere. So I'm giving you what we are at Hinsdale South. 1 atmosphere. If you were using MMHG or torr, the value is 760 at standard conditions. Standard condition for kilopascal is 101.325. And then you can move it over 3 decimal values if you wanted standard conditions for Pascal. What they don't include in the STP, but there are standard conditions for volume, because that's another variable, is 1 mole of gas is equal to 22.4 liters of gas. And these have already been solved. And again, this is us in Hinsdale South. So when you're going through problems today, I specifically have used some of these standard conditions. I didn't state at STP. Some of them I did state at STP, at standard conditions. But some of these you may see 760 mmHg, but the temperature is 35 degrees Celsius, which is not standard condition. So I don't state standard conditions unless everything is at STP. All right, well, let's do an example before I let you start practicing. I'm going to give 2 examples. I'm going to give an example. First of all, let's do an example if we're talking about standard volume. All right, so I'm going to give you, find the volume of 19 moles of gas at STP, at standard conditions in Darien. So we're assuming this is always at Hinsdale South. If I'm given 19 moles, and I'm looking for volume, volume is going to be in liters. Okay, this is what I'm looking for. I'm using a variable x to what I'm solving for. That's my first part of my proportion. I then can solve this question by using proportions, as I can for everything almost in chemistry. I can look at the proportion for standard conditions. Standard conditions say 1 mole of gas is equal to 22.4 liters of gas. So let's set that up. 1 mole of gas is equal to 22.4 liters of gas. I put liters on the bottom because I want to make sure that the units are the same, and then I can cross multiply and divide. And I get an answer of 425.6 liters of 19 moles at STP, standard conditions. So there's my answer. I'll box it in. All right, let's take a look at another problem since we'll be doing some examples with Pivnert equation, that PV is equal to nRT, ideal gas law. So a weather balloon has a capacity of 15 liters at 760 mmHg, which, by the way, happens to be a standard pressure. So at standard pressure, but I'm using 15 liters and 25 degrees Celsius. This is why I don't state STP, because it's not all at standard conditions. The pressure happens to be, but I'm using a different type of temperature. How many moles of gas is needed to fill this balloon? All right, so the variables we've been using so far, volume, right? We've been using pressure, we've been using temperature. If I had asked a question in regards to, this is the beginning, and this is how much we started with, and this, how much do we end with, you would be getting more information. But what a key point to point out is that I'm asking you a question about how many moles. The only equation that's going to allow you to solve this is our ideal gas law. PV is equal to nRT. So I'm making a point to tell you that because when everything is on the exam, it's not going to be in segments, it's going to be everything all included. So you need to take a look at the variables that you have and the question that's being asked. So I'm asking you moles. The only option then would be the one with the moles, which is your ideal gas law. So we're solving for n. So I can set up for n. If you would like to set it up before you put the values in, you may do that, or you can just put your values in. So for the exam, you're going to be expected to write out the equation that you're using to solve it, show the work, so with the values, and then give me the final answer. That's my expectation. So pressure. Pressure is 760 mmHg. So for teaching purposes, I am going to use all my units in my work. As students for the exam, you don't have to use all your units in your work. You can just use values. But I'm going to show you how to determine which R constant to use. So I'm using all my units. I have 15 liters. It's already in liters, so I don't have to convert it. And then I'm going to divide by my R constant times temperature. Let's do temperature right away. 25 plus 273 is 298 in Kelvin. So then I need to determine which R constant I need. I'm given pressure in mmHg. So I'm going to look back on my notes. The R constant for mmHg is 62.4, and that's my unit there. So I'm going to include that in my problem. 62.4 liters times mmHg, which is millimeters of mercury, divided by moles times Kelvin. Let's make sure that I'm left with the unit that I'm trying to solve for, which is moles. Cancel out my millimeters of mercury, cancel out my liters, cancel out my Kelvin, and I'm left with the unit that I'm looking for. So now I can solve the value or the problem by multiplying, and dividing. And I get my number of moles is equal to 0.61 moles. Box in my final answer. There you go. So for the exam, you'll need to show the equation. I don't care about the names of them. Remember, we're not into the names, we're into what equation you use to solve it. Show the work behind it, and then boxing in your final answer. So today's practices, practice number 3 and 4. I'm going to stop recording right now.